Welcome to the deep dive. Today we're doing a complete reset on how we think about blockchain security. It's often talked about as this, inherently unbreakable technology, but the reality is far more complex and, frankly, a lot more interesting. Our mission is a full survey, starting from the decentralized roots all the way up to the cutting-edge cyber threats targeting, huge financial systems and massive supply chains.
And that's really the central paradox here. The initial promise of blockchain, this decentralized, tamper-resistant public ledger, it was designed specifically to guarantee security. The concept itself is from back in 1991, and then Bitcoin in 2009 showed the world how it could solve that fundamental trust problem, like double spending. But the moment we applied it to more complex things, smart contracts, global supply chains, the whole security model just started to buckle.
Why? It introduced all these new vulnerabilities.
Exactly,
Yeah.
specialized ones.
Yeah. So our goal for this deep dive is to really understand that tension. We're going to dissect the foundational architecture, look at how threats have evolved from, say, simple coin theft to global supply chain sabotage. And then we'll get into the defensive tech, the architecture, and the advanced crypto that's fighting back. So let's unpack this. We have to start with the basic mechanics, right? Let's use Bitcoin as the classic example. If I, as a client, make a transaction, how does the network actually know it's trustworthy?
It's basically a massive, simultaneous competition for validation. It's a race for consensus. So your transaction goes out, and these miners all compete to confirm it. They do that by solving a really complex math problem. That's the whole mining process. When one of them succeeds, they broadcast the resulting block.
And that block gets added to the chain because it has that cryptographic link to the previous one. We often call that hash pointer, right?
Yeah. Exactly. That hash pointer is essentially a digital fingerprint of the previous block, and it's baked into the current one. Because of that chain, to rewrite history, you'd have to recalculate every single fingerprint all the way down the line, which means an attacker would need to control the majority of the whole network's computing power.
And that's what makes tampering almost impossible, at least in a well-distributed public chain.
Right.
But that security really hinges on distribution. And not all ledgers are created equal. You've highlighted 3 core types based on access and control.
Yeah, first you have the public or permissionless chains. That's your Bitcoin. They're completely distributed, no ID needed. Users are pseudonymous, and as you said, nearly impossible to tamper with. Then you have the total opposite. Private or permission blockchains, which you see in big corporations, these are fully centralized. One organization controls everything. So they're incredibly fast, and everyone has a known identity, but, and this is crucial, the controlling entity can tamper with the records.
Okay, and then there's a hybrid that tries to split the difference.
That would be the consortium blockchain. It's influenced by a set of pre-selected nodes, maybe a group of companies. So it's moderately distributed, partially centralized. It's looking for that balance between the speed of private chains and the security of public ones.
What's fascinating to me is how fast this has moved beyond just currency. We've seen these generational leaps, right? 1.0 was digital currency, 2.0 was smart contracts with Ethereum, 3.0 was broader societal applications.
And we're already hearing talk of blockchain 5.0. It's all focused on extreme performance and AI integration with platforms like Relictum Pro. They're talking about concepts like Hypernet and something called proof of czar consensus, aiming for speeds over 1 million transactions per second.
1 million per second. That raw velocity sounds incredible, but it brings up an obvious question about that trade-off you mentioned. If you're pushing for that kind of speed, are you inherently sacrificing some of that distribution and therefore security to get there?
That is the critical insight. Yes, 5.0 is an arms race for performance. But to get that speed, you often have to optimize consensus away from pure distribution. So you might get an instant transaction, but you have to ask, who's running the nodes? What level of centralization did you just accept to get that velocity? It shifts the threat vector right back toward that private chain model where a few entities just have too much power.
So if the architecture isn't perfectly distributed, that opens the door to attack. Let's start with the most famous threat against the consensus mechanism, the double spending attack. How does a hacker actually manage to spend the same coin twice using the network's own rules against it?
They exploit the longest chain rule. So the attacker broadcasts a valid transaction, let's call it transaction A, to buy something. But at the same time, they secretly start mining their own private version of the chain that excludes transaction A. They're basically in a private race against the public network.
So they make the purchase with transaction A, they get the goods, but they're betting that their private lie, their new chain, is going to grow longer than the public truth.
Precisely. Before the original transaction gets fully confirmed, once the attacker's private chain becomes the longest, they broadcast it. The network immediately sees this longer chain and accepts it as the official history, which deletes the proof of transaction A. And now the attacker can respend those coins. The double spend worked.
And I imagine the existence of these huge mining pools makes it easier for bad actors to get enough power to launch these kinds of attacks.
Oh, absolutely. If one entity gets over 50% of the network's hash rate, what we call the Goldfinger attack, they can destroy stability. They can just refuse or include transactions whenever they want. There's also another key one, especially in proof-of-stake systems. It's called the nothing-at-stake attack, where validators are actually incentivized to work on multiple competing forks at the same time, which just grinds the system's efficiency down.
Okay, let's make a critical shift here. We're moving now from attacking the ledger's rules to attacking the trust we place in the application layer, the software ecosystem built on top of the chain. This is where the really horrifying supply chain threats come in.
Yes, we saw this with SolarWinds. The attack wasn't about cracking a password. It was about compromising a routine software maintenance update, something everyone trusts. They attacked the build server itself. If you trust the vendor's code and that vendor's build pipeline gets compromised, you're just inviting malware right into your core systems.
And the reliance on open source code makes developers so vulnerable. They're constantly pulling in free libraries, and attackers know this is a huge attack surface.
And they use methods like typo-squaring. This is where an attacker creates a malicious library and names it something almost identical to a genuine popular package. For instance, they'll upload a package called Django to mimic Django, and they just lure unsuspecting developers into downloading compromised code.
And those little mistakes can scale incredibly fast, like with that massive NPM package attack.
That was a perfect storm. A developer's NPM account was compromised, and malicious versions of their really popular packages were published. These were downloaded an estimated 45 million times.
45 million. In how long?
In just 2 to 3 hours. The malware's goal was simple financial theft. It would either replace a crypto address on a web page with the attacker's own, or it would intercept the transaction request between your browser and your wallet just before you clicked sign.
Wow. Okay, before we move on, we should probably clarify what a blockchain supply chain workflow or a BSW actually is. Why does it create these new subtle attack types?
A BSW is just the whole digital process of using a blockchain to track, well, anything. Goods, services, contracts. Think of tracking medicine from the factory to the pharmacy. The smart contract, it validates the collective behavior. Did the rules of the supply chain hold up? But the crucial thing is it doesn't protect the individual local application that each person in that chain is using.
Ah, okay. So that context explains the two different BSW attack types you mentioned, internal versus external.
Right. An internal attack is like digital sabotage. The attacker modifies one stakeholder's local app, say, to provide an incorrect bid value. The smart contract can't detect it because, from the ledger's point of view, the action looks valid. An external attack, on the other hand, is a more traditional breach of a stakeholder's local system, like a customer data breach. That forces the whole BSW system to dynamically kick that breached person out of any future participation.
And finally, we have to talk about the high-stakes flaws in the smart contracts themselves. The most famous example is the DAO attack. $60 million stolen in 2016 from a reentrancy attack. Can you make that concept more concrete for us?
It was a timing issue, really, a logic flaw in how the contract checked its own status. Think of a public vending machine that dispenses money. When you hit the withdraw button, the contract starts sending you the money. But, and this is the key, it waits until after the money is sent before it updates your account balance to zero.
Ah, so there's a lag. And the hacker's contract just calls the withdrawal function again during that critical lag time,
Right.
like mashing the button on a broken machine.
Exactly that. They re-enter the function over and over before the original contract gets a chance to update its own books. It lets them make repeated, unauthorized withdrawals before the system can catch up. And that one single logical flaw was the root of a multi-million-dollar theft.
And we still see other critical coding flaws like integer overflow and underflow, which let people make huge withdrawals by confusing the data limits. Or timestamp dependence, where hackers can manipulate block times to cheat in things like auctions. So given how easily trust can be exploited at every single layer, from consensus rules to supply chain code, the traditional idea of a secure perimeter is just completely obsolete, isn't it? The foundational design philosophy now has to be zero trust.
It's mandatory. Zero Trust completely rejects that old idea of security, where everything inside the firewall is assumed to be safe. The principle is simple, but it's radical. Assume every user, every device, every system, including every single vendor connection, is potentially hostile, and you verify continuously everywhere.
That sounds demanding. If every component is potentially hostile, how do you architecturally enforce that kind of verification and limit the damage when a breach inevitably happens?
You manage the blast radius through isolation, and that requires network segmentation and even microsegmentation. You break your network into these tiny granular zones, each with its own strict access controls. So if one component, say a compromised third-party module, is breached, the attacker's lateral movement is just completely stopped.
And for preventing those crippling supply chain attacks we talked about, SolarWinds, NPM, the focus has to shift from reactive scanning to source transparency.
Absolutely. You have to demand secure by design systems. If you're buying third-party software or using open source, you need a software bill of materials, an SB-BOM. It's a complete list of every single component, every open source library, so you know exactly where vulnerabilities might be hiding. And you can audit that chain continuously.
Okay, let's talk about protecting privacy on a public ledger. This gets into some cutting-edge cryptography. How do we let the network verify a transaction is valid without revealing who the user is or how much they're sending?
We use what are called anonymous signatures. You can contrast group signatures, which need a trusted manager, with ring signatures. And ring signatures, which Monero uses very successfully, are fascinating. Any user can just define a ring of possible signers. The signature proves that someone in that set approved the transaction, but it's mathematically impossible to know which specific person it was.
So that effectively anonymizes the person executing the command. But how do you anonymize the data itself, like the transaction amount?
That's where zero-knowledge proofs, or ZKPs, come in. This is the ability to prove that a statement is true without exposing any of the information related to the statement itself.
Can you give us a real-world application?
Yeah, so in financial applications like Zero Cash, you can prove to the network that you have enough funds to complete a transfer without ever revealing your actual account balance. You're demonstrating correctness without any disclosure. It's the highest level of privacy, though, I should say. It currently comes with pretty high computational costs.
And we're also seeing encryption methods that protect the sensitive data while it's being handled, too.
Yes. Homomorphic encryption, or HE, is revolutionary. It lets you perform computations directly on encrypted data without ever decrypting it first. And attribute-based encryption, ABE, gives you really fine-grained access control. Decryption is only possible if a user's digital attributes, like their role or permissions, match a predefined policy.
Finally, let's circle back to that BSW supply chain challenge, detecting those subtle local attacks the smart contract misses. The sources propose going after the local process directly.
That's the key innovation. Because the smart contract only protects the collective behavior, the proposed method uses runtime security monitors. These monitors check what are called dynamic constraints against the local application's data. So if the local system tries to submit a bid value that's outside of a specified policy, the local monitor flags it instantly. This can dynamically enforce exclusion policies even against really sophisticated internal modifications or external breaches.
And the really critical finding was that this necessary layer of local protection can be added with almost no overhead, something like 1%. So security doesn't have to kill performance.
Exactly.
Okay, so we've covered the entire landscape. If you're building or operating in this decentralized ecosystem today, what are the key takeaways from navigating this complex world?
I think the primary takeaway is that blockchain security has to be a deeply layered defense. You need architectural solutions like zero trust and rigorous segmentation at the network layer. You need strict operational processes. You absolutely have to audit all third-party and open-source software with SBOMs. And you need advanced cryptography, things like ZKPs and ring signatures, to manage that fundamental tension between public verifiability and transaction privacy.
It sounds like there's never just one solution that fixes everything. In fact, it almost seems like the very nature of pushing the technology forward guarantees new vulnerabilities will just pop up.
That is the core conclusion. There is no single silver bullet for a secure and private blockchain. A trade-off between privacy, security, and efficiency is inherent. It's inescapable. The most secure systems require you to constantly integrate and balance these complex methods, and to always be watching for new forms of attack generated just by combining technologies we already have. It really necessitates continuous vigilance and architectural foresight, because the goalposts are always moving.
Continuous vigilance. A perfect It's a slightly terrifying note to end on. Thank you for guiding us through this deep dive.
My pleasure.